A standard X-ray gives us a flat, two-dimensional projection of overlapping structures. To isolate a specific cross-section, the X-ray tube has to physically rotate entirely around the patient, mapping out the internal anatomy slice by slice. Early CT scanners relied on physical cables attached to the rotating gantry. After completing one full rotation, the machine had to stop entirely, advance the patient table, and rotate backward to keep those cables from snapping. This step-and-shoot method made scanning slow and prone to motion artifacts. The solution was the integration of slip rings. These sliding contacts maintain a continuous electrical connection without wires, allowing the gantry to spin rapidly and endlessly in one direction. As the patient table glides through this continuous rotation, the scanner traces a helical or spiral path of data collection. Modern systems compound this speed with multi-slice CT. Instead of a single row of detectors capturing one slice per rotation, multiple rows capture dozens or even hundreds of slices simultaneously, processing a massive volume of data in a fraction of a second. Combining continuous slip ring rotation with multiple detector rows allows us to image an entire human chest in a single breath hold. We gather complete anatomical data sets with minimal motion blur, exactly when every second counts. Generating those X-rays takes immense power. A typical CT X-ray tube operates between 70 and 150 kilovolts and up to 400 milliamps. That much energy produces massive amounts of heat. To keep from melting, the tube uses a rotating anode to continuously spread the thermal load across a larger surface area, while sitting suspended in a bath of fast-circulating cooling oil. Once generated, the beam faces an anatomical problem. The human body is thick in the middle and thin at the edges. A uniform X-ray beam would severely overexpose the patient's skin on the periphery. We correct this by inserting a bow tie filter, a physical wedge that attenuates the outer edges of the beam, creating a more even intensity across the entire patient profile. From there, mechanical collimators shape the beam. The pre-patient collimator restricts the exact thickness of the exposure, while the pre-detector collimator sits opposite the patient, blocking scattered radiation from reaching the sensors and degrading the final image contrast. The remaining, correctly shaped photons strike the scintillation detectors. Inside, materials like cesium iodide absorb the X-rays and emit flashes of light. Attached photodiodes instantly convert that light into the electrical signals our computers interpret as tissue density. Every physical component hidden inside the gantry works strictly to filter out excess scatter and unwanted radiation, ensuring that only the most precise, useful diagnostic data reaches the digital matrix. Technologists control how this data is gathered, using a mathematical parameter called pitch. Pitch is calculated by dividing the table movement per rotation by the beam width. A pitch of exactly 1 means the table moves forward at the exact same width as the X-ray beam, creating a continuous spiral with no gaps and no overlapping data. Imagine you have a bleeding trauma patient who is restless and cannot hold their breath. Would you adjust your pitch to be greater than 1 or less than 1? You need a pitch greater than 1. By moving the table faster than the beam width, you intentionally stretch the spiral, creating small data gaps. This sacrifices a small amount of image detail to noise, but drastically speeds up the scan and lowers the radiation dose, crucial for a moving patient. Conversely, a pitch of less than 1 moves the table slowly, overlapping data to map exquisite detail on tiny vessels at the cost of a higher dose and a longer scan. Once we capture that scan data, we dictate how it is rendered using 2 fields of view. The scan field of view is the entire physical area the scanner collects data from, but the display field of view is the smaller, targeted area the software actually renders onto the monitor. This brings us to a strict mathematical relationship. Pixel size equals the display field of view divided by the matrix size. If we shrink the display field of view around a specific organ without changing the matrix, the resulting pixels become physically smaller, granting us much higher spatial resolution. Manipulating parameters like pitch and field of view allows the technologist to constantly adapt the machine, balancing the strict demands of image resolution against scan speed and patient safety. Even with perfectly calculated parameters, human anatomy poses a final physical challenge. The density of an air-filled chest requires drastically less radiation to image clearly than a thick, bone-dense pelvis. Modern scanners automatically use Z-axis tube current modulation, constantly reading tissue density. It drops milliamps through the lungs, then spikes power for the abdomen. Within the X and Y plane, it decreases power across the thinner front-to-back profile and surges through thicker lateral shoulders. This summary table organizes the physical hardware on the left, like multiple detector rows and bow tie filters, against your controllable parameters on the right. Notice how increasing pitch predictably decreases your dose and resolution, while shrinking your display field of view sharpens your final image. Modern CT scanners deploy intense computational power to adapt to the patient automatically. But it is the radiographer's precise control over the physical variables of the machine that guarantees an accurate, life-saving diagnosis.